All right, then let's get started. It is my great pleasure to welcome Wing-Kam Liu to the department. So Wing-Kam is the Walter P. Murphy Professor at Northwestern University in the Department of Mechanical Engineering and the Theoretical and Applied Mechanics graduate program. So Wing-Kam earned his graduate degrees from California Institute of Technology, where he was Tom Hughes' first PhD student. Wing-Kam has, during his celebrated and distinguished career, Wing-Kam contributed to almost any area, any aspect of computational mechanics, including shell elements, Lagrange and Eulerian formulations, very important mesh-free methods, and most recently multiscale materials modeling with specific application to additive manufacturing. Then Wing-Kam published a large amount of papers and several books, including the classical textbook on nonlinear finite element methods for continua and structures with Ted Belichko and Brian Moran. Wing-Kam is a Thomson Reuters highly cited researcher, and he also served on the other side, so he's the editor of two journals, including the Springer Journal Computational Mechanics, which belongs to the three top journals in the field of computational mechanics. Then Wing-Kam's research has been funded by multi-year, multi-million-dollar projects, both from federal agencies such as DARPA and industry, including Bridgestone and Goodyear. Wing-Kam has won a large number of prestigious awards. The most recent ones include the Gauss-Newton Medal from the International Association for Computational Mechanics, the Henry Thurston Lecture Award from ASME, and the John von Neumann Medal of the U.S. Association for Computational Mechanics. Wing-Kam has also distinguished himself by serving the scientific community, for example, as past president of the U.S. Association for Computational Mechanics, and Wing-Kam is the current president of the International Association for Computational Mechanics. So here I would like to stop. It's my immense pleasure again to welcome you to the department, and we're looking forward to your lecture. Thank you.
Thank you. I'm very delighted to be here. First of all, I'd like to thank the Warren Lecture Committee, in particular Dominic, invited me to give the lecture. And I can see your department has a lot of good talent. And just by judging how Dominic can remember so many things about me which I don't even know about, and that's fantastic. You know, thank you, Dominic, for introduction. So I usually like to come to give lectures, not just because I want to talk about my work. I want to recruit good students. So for those good undergraduate students who want to know more about Northwestern, please come and see me. Sorry about that. Yeah. So that is the way I recruit good students and postdocs, and that's the reason why I can give good talks. Hopefully, it's a good talk. So today I will talk about a couple of things. I'd like to focus on mechanics. So self-consistent theory is a micromechanics theory. So that's the reason I picked self-consistent. Now, clustering analysis is something that we borrow from image processing, data mining techniques, mostly from computer science. So we basically borrow the idea, for example, the one I'm going to use is called k-mean clustering. The whole idea would be, which is based on fingerprint technology, is look at a pattern. Okay. So now if you look about self-consistency, which is a micromechanic theory, I'm focused on microstructure material. Basically would be, within a material you have a lot of microstructures. So when you do a stress analysis, you look at a strain field, stress field, you should have some similarity patterns, just like the fingerprint. Okay. So we borrow that idea called clustering analysis. So that's the reason I call SCA, self-consistent cluster analysis on this screen here. The whole idea would be, instead of looking at a tremendous amount of detail or information from a numerical analysis, such as finite analysis, I look at clusters. Okay, so now I can reduce the computational effort by focusing on solving the cluster problem, which is a reduced order model, okay, and for material design. Now, so then then bring into the other thing is called data-driven. So data-driven would be, we do a lot of analysis, we do a lot of experiments, so we have a lot of data. The question would be how I'm going to leverage both experimental and computational data for design of material system. Okay, so that's where the last two words is, of course, would be multiscale is a buzzword. So I just put in there called multiscale material. So that's my talk. But of course, it would be, this is not done by myself, done by a lot of students, postdocs, and professors. For example, Mark Fleming is one of our former graduates. He basically do witness consulting, so I learned a lot from him. How to look at important problems, what to look for when you do witness consulting, look at failure analysis mostly. Greg Olson is material science. I mean, I would call him computational material science, the father of computational material science. He started a company 28 years ago, maybe more than that, called Questech. Maybe 3 or 4 years ago, he sold 50% of the company to Apple. He can retire, but he decided not to retire. He told me, I need your help. He wanted to rebuild his company. So he rebuilt his company in less than 3 years. And that team went to Apple and designed new material for Apple within 18 months. So we have a new design that they cannot make the material to do that is related to the the watch. Okay. And then this guy used to be president and CEO of the company called Charlie Kuhlman, recruited by Elon Musk to become the vice president of material research for both Tesla and SpaceX. So that's a success story that I think the undergraduate student, please come to Northwestern in this case. Okay, Professor Jane Chow is a manufacturing person, so I learned a lot from her on the additive manufacturing aspects. So what is multiscale mechanics material? Okay. I like to put this, it will be simple as you see, but more complicated than you think. Let me explain to you what it means here. So we started the Nano Institute, Nanomechanics Materials Institute, maybe about 15 years ago. So my colleague, Professor Yiba Chung, make an experiment. He make a piece of ice, he drops it, it breaks. And then he reinforce it with a Chinese newspaper, crumple up, in particular with black and red, okay? And then you can see it drop it, okay? It doesn't break. Everyone knows this is called composites, okay? But if you shrink this to nanoparticles, micron scale for red, black would be nanoscale, then you can have a 2-scale with a matrix material design problem. So I want to just focus on this, talk about design of this material. There are many different names on this thing here, but I will not go through history on it. But the whole idea would be, it's a very simple problem, but you can make this problem as idealized as you want or as practical as you want. Okay, so talk about 3-phase material, but then there are a lot of chemistry, processing, everything's involved in this case here. I don't know what happened to it. Okay. So the whole idea, but you can use this as an imagination, how you're going to design your material system, how you're going to process a material and so forth, and how you're going to select your matrix material, your inclusions, whatever you want in this case. There are a lot of chemistry involved also in this case. So let me give you one example. This one is the one that we did for DARPA, actually the Questech project. That would be, it's a blast resistant material. So basically it would be, that was a long story, but I will not go through this one here. Would be, we want to strengthen blast resistant, that means toughness, by designing, originally, Greg Olson put in nanoparticle on carbides. So it's titanium carbide, basically. It's like nanoscale, like tens to 100 of nanometer scale. So you have a lot more surface area. They design the chemistry of it, so they have a lot more debonding strength. But unfortunately, you have this nitride. It's a byproduct, which is in micron scale. So we have a 2-scale material. So of course, if the ice now is my alloy, whatever alloy that is existed system, but the original goal is to design the carbide, but with a byproduct of nitride. Okay. Now, so the material science say will be this controls everything. Okay, I say after 5 years, we say no, not quite the case. Okay. So what we did will be we do a lot of multiscale analysis. I want to go through history and look at different length scales of the system. And these are very detailed calculations on it. And the whole idea was this bring into non-local theory in terms of mechanics. I want to focus on mechanics in this case here. You can see it will be very different length scale, many length scales. So we come up with length scale theory for this particular problem. And the whole idea here would be we want to understand and predict performance and failure limit of advanced material. And of course, it will be safety and integrity. And of course, now you need to think about what methods, or what computational approach, what experiment we need to look at this problem. Okay, so that's one example. So let me give you, an outline what I want to talk about. So I will talk about, give you a general framework, the data-driven modeling of multiscale material. And I'm going to focus on a new method that we developed, okay, called self-consistency theory, based on offline database and online corrections. So the correction is based on a mechanistic way to do it. Unlike what people do will be based on mass amount of data, they just learn the system and predict. Okay, so our prediction is based on mechanics. So that's what the focus on this particular talk. And then we're going to apply to a number of important problems. And then I will talk about concurrent calculations, which is like finite element square, for example, but using this framework to look at it, and I will draw some conclusions. So the whole idea would be process structure property. That's a material science framework. And there are a lot of different theory that you need to know to understand from process to structure, but I will not talk about this today. You can invite me back if you want. Okay. And then we talk about structure properties. I think that is the one that I'll focus a lot more on. Given the process, given structure, how I'm going to predict the properties. So that is my focus in this case. Okay. And then, of course, there are a lot of different techniques. So it's a teamwork. If you talk about material system, you cannot do everything by yourself, but I focus on one method that would link structure to properties using a data-driven approach. Of course, it would be the whole circle is the key for what we design, material system design for corporation or for big projects in this case. So I'm going to put down 3 challenges. The first challenge would be efficient concurrent simulation. Like I said, we are interested in a lot more dynamics, okay? And you cannot do hierarchical. Basically, it will be because a microstructure influence one another. So I want to focus on how we go link them together to do concurrent calculations. And if you look at some problem that I was talking about, would be one is a biomedical stand. We want to design this for fatigue. Typical material microstructure, and this is our latest project with Ford Motor. Instead of using alloy, we want to do composites in this case. So you can see there are different kinds of microstructures. I will not go through the detail on it. In fact, this one is the 787 composite material, which I got one piece from United Airlines. On here, I took the picture of that one. But we're going to get a cheaper version of this for this particular one. Okay. And how does the process affect the microstructure? And how does a microstructure affect the properties? So I skip process structure. So I just say basically it would be process go directly to the properties in this case. So in this case here, with the requirement for my challenge one would be accuracy, efficiency, and reliable. And most of the finite calculations are mesh dependent. I want to make sure it's non-local. Okay. So what is involved? The key thing would be, look at this microstructure. How big is this I need? Okay, that's a theory from statistics would be you do many samples. For example, do a smaller sample, you have a larger deviations. When you go down to here with p value equal to 5, that means 5% variation for standard deviation. Then you say that's my RVE size. That's a critical definition. So you actually go through statistics. We have a person work on statistics, understand exactly what we need to get it correct in this case here. Okay? So this is the way we define that, and then the question would be homogenization. Everybody do that. Okay? The question, how do you do it, and how does this non-local interaction would change your design in this case here. Right? And for this, I'm going to come up with the data-driven self-consistent clustering analysis approach to compute the material laws. Key thing is we found an explicit expression on the fly. Okay, so that means I want to do a very complicated RVE, but I want to do it in very short time. So you cannot do it with direct numerical simulation. So that's what my focus on this talk, on this one here. Now, based on this thing here, I can give it back to, there are a lot of different theories in non-local. Okay, I will not go through this. One way people talk about periodynamic, reproducing kernel, all kinds of stuff. We use a lot of this kind of techniques to solve the problem. But the whole goal I want to say here would be, I want to translate this mathematics into physics. The properties is the principal virtue work at a corresponding material point. You can think about this, my material point in continuum mechanics, but it goes through two sets of microstructure, which I explained to you earlier. And this principal virtue work has to account for all this information. That's stress times strain, okay? And the structure is this microstructure, is the non-local interaction of the microstructure cluster. So basically, you need to homogenize this to put it into here. So that is my definition of homogenization from structure to properties in this case. Okay, core challenge 2 is homogenization with localization. So these are pretty well known in finite element analysis. Okay, and you can see here would be this one is mass dependent. This one is size dependent. So you need to understand what it means by that. And if you go to localization, with the classical way to do it, this is mesh dependent. This is still size dependent. So today I'm going to focus on using a very traditional theory that we borrow to see how I'm going to look at this problem. Okay? That's my challenge 2. And my challenge 3 would be localization with size effect. But what does it mean by size effect? So I go back to here. The angel material has random sizes, random length scale. Okay, and what we'd like to do would be, we have done a lot of work on length scale theory, multiple length scale theory that can do concurrent calculations. Okay, but I'll give you back the same example. If you look at this particular problem, if you do the experiment or do the simulation, you can see minimum I can find 3 length scales. But you can find as many length scales you want, depends how detailed you want to understand the problem. But for this problem, I focus on 3 length scale, but I'm going to only talk about 1 for this lecture. Okay. And the next thing would be size effect. Okay, it's very important on the size effect. Okay, it would be most of the theory talk about volume fraction, 1 parameter. But this problem I illustrate would be with the same volume fraction but different sizes, you get different response. Not just look at the shear band, but look at the deformation. So it does change your strength and toughness. So that's where the material science comes into the picture, how we can incorporate the size effect in this case here. Okay. So again, it depends on what kind of approximation you want to understand before you develop your theory in this case. Okay. So there are many gradient theory. You can actually come up with gradient theory to do this kind of problem. Okay. And I'll give you another example would be, this is tungsten carbide material for drilling materials. So like right now, there's a lot of people talking about, how to drill faster, but at the same time do not break the material. So this tungsten is very strong, but it's very brittle. So you put in certain percentage of the carbide, which is no, first a cobalt, which is a lot more ductile material, then you can actually really do a lot better in terms of the performance of the system. But for this one, you can find out your falling scale. So you really need to understand the material science aspect before you can solve the problem. Okay, let me go to my theory. Okay, so far I'll give you motivation. What we're interested in is we need to understand the material behavior before we can develop a theory. You cannot just develop a theory for any material. What we focus on will be material-specific theory in this case. So let me talk about this particular one here. There's some reference here. This one just got accepted. Should be online pretty soon on data-driven design. Okay. So I'll give you a little bit outline what it is. Okay. So we do a concurrent self-consistent clustering theory. That's what I gave you earlier. So that the name comes from. And I want to talk about will be efficiency. We're going to set up database, computational experimental database. But for this talk, mostly computational database. And then I'm going to do correction using an equation, Liebman-Stringer integral equation. Actually started from quantum mechanics and then used in many other fields later on. We're going to borrow this theory. It's a pretty general mathematical theory that we can borrow. And then we're going to do computational experiment to design material, in this case, material system in this case. So the outline basically is like this. You can think about would be for just put one inclusion for illustration or do a 3-layer of composites. Okay. What it would be, I can say I do a direct numerical simulation, which is my represent volume 80 by 80 by 80. That's pretty big size. I'm going to say compress this using this k-mean clustering, 16 cluster. So instead of solving 80 by 80 by 80, which I need to do, but for a database, I'm going to go through this theory, come up with the interaction tensor, which is a standard micromechanics theory, 16 by 16 interaction. So now I reduce this system to a 16 by 16 system for this particular RVE, for one material point. But there are many, many material points in your whole systems. Okay? So that is one way to look at it. Same thing for here would be, for this composite, I do 160 by 160 by 20. I'm going to use 16 clusters, just for illustration. But we do power of 2, 16, 32, 64, and so forth. Okay, but the computational cost definitely is a lot more. Not only that would be, we pre-compute all this database for design purposes. And then we use this Liebman-Stringer equation to correct it. So you can see the computational cost. Now basically it will be, you can use, the database depends on how well you understand the system. For illustration purposes, I'm going to just use elastic, because it's very simple to compute, and I can do plastic, okay, on it, but still not correct, so I need to correct them on the fly using this theory in this case. Okay. But the computation is, instead of this, I'm using this. Okay. So I will not go through the algebra, but this is an academic seminar, so I need to put down some equations. So the whole idea would be, the first thing I want to do is something called the A tensor, which is called the concentration tensor of micromechanics. And you compute the microstrain as a prescribed macrostrain. Basically, it's the boundary condition from your macro scale calculation. You put in 1 here, you get this A matrix. Put 1 here, you get this matrix. And then you get this one. So that's the way you get here. Now you can get a really set of data. Based on this data, then I can use this k-mean clustering technique to look at the interaction tensor. Again, will be this another theory that we borrow. Okay? And I want to go through this, give you an example here. I have the matrix material using 1 cluster, 16 and 256 for the matrix, and for the inclusions, I use different cluster. Just give you the illustration. So this is the choice of theory. And you can see the matrix in the inclusions. So top of 2. So the interaction tensor is based on this. So I will not go through mathematics on this. It's pretty standard thing. The only thing we do is put in clustering in this case here. And then you can see here will be the interaction. It's like this. So you can talk about matrix to matrix interaction, matrix inclusion, inclusion. Now you have come up with this interaction matrix. That's the way you derive this interaction. Now I can do a reduced order model instead of doing a large-scale computation. This is something is my learning process, I call it. Okay. And then I use this equation, which is a green function equation. Okay. And actually, the pioneer is Pierre Sicard, French mechanicians. And we borrow this and compute the corrections. I will not go through the theory on this thing here. And then you can see all this equation. You compute, that one is offline, and you apply this boundary condition. So these are some programming involved on it. And then you basically come up with a corrections, and this lead to my theory in this case. Okay. Like I said, I will not go through all the equation, but I'll show you there's some equations. So I'm a professor in this case. Okay. So give you some illustration. Okay. I will start with elastic plastic material. So we do two kinds of material. One is a fiber reinforced composite in a plane. And then we do the amorphous material. This is a lot more based on phase field calculations on it. And you can see will be how the convergence is. Okay, one cluster, 256 compared to a very detailed calculations of it, and that's the size we're doing here. The DNS is 600 by 600, and I use the clustering, but this is 2D. Okay, so the speed up is in this 2 order of magnitude in this case. Now, of course, it would be people ask you, you pre-compute a lot of stuff. Yes, we do. But that's for my design problem. But it depends on how detailed you look at your characterization of whole structure. That is statistics. Okay, that is something would be, most people just compute once. They say that is for the whole system, but that's not true. I can give you an example would be, if I want to do functional gradient material, you need a lot of microstructure because they're changing, basically. Okay. In particular for additive manufacturing, you cannot assume one set of microstructure will give you the whole thing. So you need to combine with some kind of distribution plus extreme events. So that we need to think about how to apply extreme event theory to do this kind of problems. But you're not going to compute every single point, but we do compute enough that we can understand our system in this case. Now, you can do very complicated loading system. Like I said, we don't really have explicit material law. And the key thing will be, we can say here will be, I start with loading in this direction, loading in that direction, and come back this direction. So that is my computation. If you look at here, this is loading 1, 2, 3. Okay, so you can do actually arbitrary loading, and we can compute it close enough on the fly. That means instead of thousands of seconds, I can do it in 1 second. Okay, of course, it's not really real time yet, but if you can get it learning much better, you would go to real-time calculation. That's what I want. Okay, so in the 3 dimensions, you can see the speed up. Okay, these are done by students, so I will not take this literally, but we talk about order of magnitude in this case here. Okay, but for 3D, it's cube, so they can see the computational cost definitely will make a big difference in this case. Okay, let's just talk about apply this to a problem on fatigue. So we are designing this particular material. Okay, there are many processing problems. Okay, I will not have time to talk about that. And we are talking about this particular artificial valve, which is nickel titanium. Oh, I hate that. Okay, and then go to here. Most of the valve, or actually medical stand, I don't think this is ready yet, would be failed by fatigue. And it's very hard to remove it. You cannot remove it. So they need to go to a different one. So it's some patients have multiple stents, okay, because they are basically stuck in there because of fatigue. Okay. So the key thing would be For metallic, we want to design this to 20 years. No material yet so far. So that's what at least Greg Ocean want to look at this part here, but he need a theory to do this. I will not go through the detail here. So the whole idea here would be you need a concept how to design a material. Okay. If you look at a microstructure, lots of microstructure. Okay. So the whole idea here would be this process is based on a bulk, forming of the nickel titanium, and then they do extrusion, okay, to get the shape, and then they use laser to cut the shape they want. That's a typical way to make this problem. Okay, but there are many other processing, which I will not go through a detail on it. But the whole idea would be, if you go through what I just tell you, you do the bulk modulus, bulk forming, extrusion, and if you have the inclusion in here, you can see the called stringers. Very well known in this industry. Okay. The question would be, how do you define where the stress concentration is? How are you going to define fatigue? In particular, there's a theory called fatigue indicator parameter. How are you going to search for it? Nobody knows. Okay. Now, is that the right theory? I don't know either. But the material scientists tell me that is the right theory. But I need to come up with a way to design the process. Okay. So let me tell a little bit about what I know, but it's a tough problem because they don't share the secret view. So you need to guess what they're looking for. Okay, so the stringer acts as an initiator site for fatigue. Okay, but that is the assumption. Whether it's right or wrong, I don't know. If you can guess it right, you're in good shape. Okay. So we do a lot of actually experimental work. In fact, we have some time from the APS system of argon. In fact, we do a lot of experiments, but not me, but my student. Every time we send about 6 students there to do 24/7 for 1 week. That's all the time they give it to you because they only have 52 weeks to use their facilities. Okay, and so I will not go through the detail. Again, basically a similar theory, but now we look for prediction of the fatigue life. Okay, and the key thing is to identify the worst case, but I'm not sure that's right either. But that's what I'm told. The question will be how are you going to skim through the whole structure, look for the worst location. Okay. So of course you need crystal plasticity. So that's another field that is not easy. Okay, because when you actually do processing, there are a lot of dislocation. All kinds of dislocation theory, and they change everything. That's where the plasticity come about. So you need to know a lot more about the material science aspect of the mechanics. So again, you need to think about correction. So in this case here, I'm going to use a plastic strain tensor to do my learning process, to do K-mean clustering. And then, we use a small cluster because this is a very expensive calculation. This is crystal plasticity. Using 16 cluster, 32 to get the scanning. And then when you get down to there, we go to a lot more cluster or even DNS to verify it in this case here. So for this thing here would be, this theory again would be, this is a very famous paper that we borrow. Okay. Whether that's the right one or not, I don't know, but that's what everybody believes in. So we compute this something called the fatigue indicator parameter based on this theory. And the whole goal is to design the B2 nickel titanium austenite with 12 slippers. So very, very material science theory on this part there because that's where the material design comes into the picture. Okay. And identify the worst case, that means minimum life microstructure. And of course, these are very large scale computations. Okay. So let me show you a little bit about how we're going to design this process. We do have one person retired from Medtronic. So he now is our consultant to look at this problem. In fact, Carl McVeigh, you know him, is working with that company right now, and he tried to work with us, but the VP say no. They don't want to share any secret whatsoever. So, but anyway, you can see here would be, I just do a very simple model to demonstrate we can actually do something like this. These are idealized materials, no real material system because they won't tell you anything about it. So we probably either do our own experiments or to do it. And the whole idea would be, we start with larger inclusion, because make small inclusion is very expensive. So we start larger inclusion, try to process to break it down into very, very small one, and that's where the string comes into the picture. Now that is the hypothesis. What is the right way, I don't know. So we need very smart people to come with the concept, how to design a material in this case. But we do have the capability to look for it if I can get the original shape correct. Okay, so that is a lot more would be experimental driven, data driven approach, look at this thing, but we can develop tools to solve these kind of problems. Okay, first of all, you need to understand the experiment, and then you need to understand how to model it, and then you apply this theory. Okay, so there are a lot of different steps you need to get involved, and these are all predictions. You can get any number you want, but the question, which is the right answer? That is the key point. You know, would be, we can actually say increase my fatigue life. You can see here would be versus, you can see, but we talk about 2 order magnitude difference. But in this one, that's pretty good actually, in terms of computation. To give you a quick estimate on this. Okay. I just highlight a little bit would be another way to look at this using additive manufacturing. Then you can avoid a lot of problems. Okay, you can also do chemical vapor deposition. So there are a lot of competing ideas. So whoever comes with the best idea, get it out to the market first, that guy is a winner. So that is the hard part. Okay, so you need to find the right team to work with. In this case, I'm not sure I found the right team yet. You know, so. But anyway, so we do a lot of imaging. So this is based on additive manufacturing. We use the argon system. I will not go through all this thing here. And you can see this is 2 weeks of 6 students work 24/7 just to get the data. So we are starting looking at the data, okay, on it. And based on this experiment, we need to go back. We're just learning how to do the experiment and how to interpret the experiment. And this is the message. Okay, that's what we have. But it's not too bad because we only talk about 2 weeks of the APS time. But we got lots of data. It will probably take us a few years to analyze this data. But is it worthwhile to look at this data or work to the next data? That's a decision we have to make. Okay, but for students, it's fantastic because they learn something. They learn a lot in this case. So I'm going to go to the last aspect, the last core challenge. Okay, would be softening. Softening is well known in here. The question would be, how do you do softening? Okay, so if you look at the material science, this is from one of my, this is from a thesis, but then the guy followed this thesis, and now he's working for me. So the whole idea would be, if you look at the force displacement curve, there are a lot of microstructure evolutions. So these are cumulative many PhD theses learning and come up with a better theory for it. Most of them are actually from Europe. Okay, so this is from this guy's thesis. Just you can see here will be he developed level set all kinds of fancy theory that can do very detailed computation of brittle buckling, fracture, fragmentation, and so forth. But it takes, like I said here, multiple days to just look at a small cluster like this. There's no way you can do it for design in this case. But very detailed analysis, very nice analysis. In fact, they actually do digital image correlation, digital volume correlation to verify his calculations in this case. Okay. So, because the brittle material, you know, he basically do homogenize a micro cracking because it's a mechanism for brittle material, and he's thinking about using the technique that we develop. Okay, no here. Yeah, that's right. Okay, so here, So let me talk about this thing here. If you do one-step procedure that everybody does, okay, do a very simple illustration using classical damage mechanics, which has no physics. Okay. Elastic material, you put a damage parameter. The question, what is a damage parameter? Okay. That's a very well-known method. And this is the way you compute the system. But like I said, you have the localization, you have the size, you have this. Okay. And you need to separate the plasticity and damage. So that's our proposal in this case. So basically it would be, we define this elastic plasticity without damage as a reference plane. So the first thing I need to do is compute this one. Okay. And then I'm going to break it down into 3 steps, but we'll not go through in detail because the paper is not published yet, and this is one person's thesis, part of his thesis. So basically it will be, we break it down into 3 steps because you have micro, concurrent calculation, micro, macro, and then you basically start from here, you want to go back to this law. Okay, so there's different theory around it. Now how good it is, I don't know yet, because very hard to do experiments on this, because the damage theory is not really the right theory, but that's the way we develop the methods in this case. Yeah. So I will not go through detail on it, but break it down into 3 steps. Okay, so that is the standard homogenization theory, but instead of 1 step, I break it down 3 steps, and you can see how it works. So there are 3 constant equations. One is the reference without damage. This one is without 1-step calculation, you get localization because you expect that. Mesh-dependent results. And this one is mesh-independent results. Okay, so this is just a numerical analysis, have nothing to do with the physics. The question, how are you going to relate the physics? Because people, industry or engineer like to get the simplest law, and that's the simplest law you can do. The question, what is D? How are you going to calibrate the D from the real material? Okay, so, so this is actually to show you how the computation is being done, and you have no numerical issues at all in this computation. And this gives you a lot of physics, how we actually construct the system and why we want to break it down to 3. It's a little more computation cost, but it's worthwhile because I don't have numerical issues. Okay, so this is just some convergence study, but the whole idea here would be we go bring in the non-local theory. I guess there are a lot of Bazan former students here. I'm going to put down Bazan's theory here. 87, non-local theory. Okay, so the question would be how we go bring this non-local theory that has a physics. Okay, because this is all mathematics. A lot of people confuse the physical length scale versus the mathematical length scale. These are all mathematical length scale. You need to calibrate the right physics. So one proposal, I go back to my problem, is right here. I know my physical length scale, either from experiment or from computations. Okay? And not only that, I know my size scale. So I have 2, size scale. Direct numerical simulation can get you the right size scale, but you need to know how to put that in. Okay. So based on this thing here, we can actually come up with a very simplified problem, and this is a bad problem. This will not be published as is because we have a singularity here. Okay. But you can see here would be how this low diffraction curve as a function of the microstructure and damage propagations. Okay, so this is something that we are just finishing up this paper. And the whole idea here would be we want to have a physical meaning for how to do non-local induction related to the physics of the problem. But of course, it would be you either really believe your mathematical model is correct, get the DNS calculation to understand the problem, you put it into your model in this case. Yeah. Okay. Or you do experiments, either way in this case. So these are something that we do convergence study, mesh independent result. These are pretty standard numerical methods in this case. And the key thing would be, I give you an idea here, would be look at the hard inclusion versus soft inclusion. They give you the same behavior. I'm not sure this is correct either. Okay, so these are all predictions. And you can see the difference will be they all go around same, okay? But one is delayed and the other one is not. And if you look at a little more prediction, they have different angles. So the question would be, is it really 45 degrees? I can basically tell you, I want to design a material that at any angle I want. Not only that would be, I want to look at how design versus triaxial versus shear, all kinds of loading conditions to design the type of behavior that you want, in this case. But that would be a lot more understanding of material. How do you design material in this case? So I'm going to go back to my newspaper problem. So basically it would be two larger black newspaper, the rest are red newspaper. Now go back to nanoscale. And this experiment we did, we looked at the process, and you can see here would be how the fracture process is going to go about. Even though it's a mode 1 fracture, you get mixed mode fracture. So that's the reason why you can actually get into the toughness in this case. So that's where the process zone is. This is done about maybe more than 8 years ago now, okay? But at that time, you can see we actually solved up to about 1 billion equation, 2 billion equation for this problem, okay? DNS calculation. I'm going to apply this idea back to this problem. And the whole idea here would be, these are material by design. Now, this is 3-link scale theory. So you can see we have shear band within shear band, and the question would be, how do you actually, now instead of using direct numerical simulation to do this problem, can I apply what we have developed after 8 years, go back to think about this problem, to do a little bit better on it. And of course, now we have better experimental techniques. And you can see here would be, now this is a concurrent calculation between macro and micro. I think it's the movie is moving, right? I think so, right? If not, I need to go to here. Maybe I just try it one more time here. Yeah, now it's moving. So the whole idea with this is something that when we do the experiment, I have the statistics of the initial microstructure. I fracture it. I have the final microstructure, but nothing in between. So you need a theory to predict this. So that is something that would be, this takes days and months to run, because there's so many calculations. Make a lot of assumptions. Now with this theory, hopefully we can see a lot better in 3D calculations on it. You can see very slow process. The whole experiment is about 1 minute to look at the fracture process on it. You can see the whole idea, how can we design the microstructure to give me the most complicated fracture process, to give you maximum dissipation in this case. So that's what we want to look for. And this future material we're working on, mostly related to additive manufacturing. This one is from Caltech. It's a nested microstructure system. And I think Julia Grill and Dennis Couchman are working on. We have a proposal together on this, and a lot more on different kind of applications. So we are basically problem specific to develop methods to solve this kind of problem. Anyway, that's my summary. I basically talk about one theory called self-consistent clustering analysis. Okay. And it breaks down into the offline training stage, and then we do the accuracy is correction. Basically, do correct on the fly using Lippmann-Schwinger integral equation. In fact, we are mostly based on a static one. For the dynamic one, for the time integral, that is a very tough problem to solve. So I'm looking for somebody who can help me to solve that problem. What we do here will be, we do integration of microstructure reconstruction And high fidelity multiscale prediction of the data material leads to generation of larger data. How are we going to use the data? So we just started. So we have another member doing machine learning and how to look for, extreme event and do some kind of predictions on it. And of course, uncertainty is very important in this case. Yeah. The structure probability feedback loop enables to design a new material system with new capability, but you need to really know what you want and come up with a way to design the system before you do the theory, but we develop certain tools for it. And in mathematical physics, I interpret the structure as the non-nodal interaction of the microstructure clustering. So the more interesting clustering, the more capability, the more flexibility you have, but you need very accurate and fast computation or analysis technique for this. And after that, you can call this homogenization, and that is a structure or the properties. Then we interpret that as the virtual work at the corresponding material point. So that is related to mechanics in this case. I think this is my final line. Computational design experiment, that's a key point because you cannot possibly design all possible ways. So design experiment. But when I say design experiment, it doesn't have to be physical experiment, also computational experiment. So you can do a reduced order model, and by that, use data mining technique to look for which are the more important information. And combining this will offer the ability to discover the influence of microstructure on the macroscopic property behavior. Thank you.
Thank you. So I'll be conducting a question and answers part of the presentation. So please identify yourself, and I come with a microphone. Questions?
Do you think of non-local material as something that we use basically to get rid of mesh dependency, basically to be able to solve the problem, or something that is physically happening?
Okay, so I break it down the question I answer the question in two different aspects. In mechanics, we train students based on mathematics. Not that many students know material science or the mechanics of material science. So most of the theory developed has imaginary microstructure, imaginary length scale, imaginary non-local theory. But that's very important because you need creativity. That's the reason why the mathematics is so important. Mathematics, mechanics, mathematical physics so important. So we borrow those mathematical assumptions. But now we want to apply for a real problem. Okay? Then you really need to work with material scientists or you learn yourself. What are the physics? What are the material science? And try to put them together. I hope I answered that question. So there are two separate understandings, but now you need to put them together. How are you going to interpret the equations? How I'm going to put the physics into the equations. Right. So that I'd like to explain in the terminology that mechanicians understand is non-locality. But the question, what does it mean in the material science? The simple example I'd look is the interaction of these particles. You can think about it's well explained in micromechanics. Because, for example, would be if you have a major crack with some micro crack, depends on arrangement of micro crack, you have shielding effect or your amplification effect. That's interaction. You can call it non-nodal interaction. So it depends on how you interpret the theory in this case.
I'm not sure if that's a good impression, but the impression that I have is that in your homogenization part, you deal with properties, with the materials that are on the global level isotropic. Is that correct?
No. So, I mean, would be homogenization is a mechanics terminology. To put in the material properties, you really need to put in the real material properties. Say, for example, for a problem, we are working on the 3-scale steel design for blast resistant. The material is a very complex material. It has more than 20-something composition. But we use that as a reference frame. We do testing to get the material properties on it. So it's well-defined material. But now I'm going to add in this design material, titanium carbide, with a byproduct with titanium nitride. So I measure those, I characterize those, and put in this model. And that is my new material that added into the existing material.
Yeah, that's the way it should be, but my impression comes...
Well, that's the way we do it.
No, yeah, I understand, but my impression comes from the fact that Lippmann-Schwindler equation, for instance, uses green function, right? And if you have, and the green function has to be for some homogeneous material that you are using there, right?
Yes. You can think about would be my original steel consists of more than 22 composition. I model as a homogeneous material.
I understand that. So that's the idea of homogenization.
Yes.
But if you need a green function, do you have a green function for anisotropic materials?
No, I have the green function for the basic matrix material, but now I add in all these inclusions in. So that is my assumption using this theory. Now, of course, it would be if someone gave me a better green function, I would take it, yes.
So you assume that your matrix is the reference material that you
The reference material,
and it is isotropic.
Yeah.
Okay.
So that one we can do by measurements or by computation, but those are well-established material. Yeah.
So I take a liberty to make a comment that there are green functions for anisotropic materials as well.
Yeah.
Yes.
But for material design, the whole idea of material design would be try to use superposition. Now, how much superposition work is the interaction, again, non-locality. So that's the reason why it would be material scientists design material, the smaller the better. Now, whether it's true or not, again, would be, that's assumption right now, because you can use superposition, because the whole idea would be I design one particle for one function, right? So it depends on make your approximations. Yeah.
Well, maybe one last question, if there is any. If there are no questions, let's join me in thanking.
Thank you.